In my lecture today, I want to derive the centripetal force equation for you. Now this accompanies section 5.7 in your textbook, Matter and Interactions, and a lot of the figures are from that text. So basically, let's say that we have an object that's traveling along with some initial momentum, indicated here by this blue arrow right here, okay? Now, something happens to the object, and it goes through some change, and so its momentum changes. Now, there's a couple of things that can happen. Either the magnitude of the momentum can change, or the direction of the momentum can change, or some combination of those two things, right? So we can see here that both happened. We had an initial momentum that was mostly, say, to the right, and then the object sped up, indicated by an increase in the length of our final momentum, right, arrow, and then it also turned upward, so the direction changed. Now this was obviously caused by some kind of force, because anytime you have a change in momentum, that's due to the force via Newton's second law, F is equal to dp dt. However, at any given point in time, the force on an object can have components parallel to its current momentum and components perpendicular to its current momentum, as shown here, okay? So here we have this initial momentum vector, and you can see that there was a force acting on it at this instant in time that was kind of up and to the right. If you break that down into parallel and perpendicular components to the direction of motion p hat at any given point in time, you can see that there's some components parallel, and the parallel components act to speed the object up. And then it also had components that were perpendicular to the current momentum, and that opted to turn the object, okay? Now we can write the total force in an object as the sum, the vector sum, of its parallel and perpendicular components, as is shown here. F is equal to F perp plus F parallel. The subscripts here indicate perpendicular for the little upside down t, and parallel for the two parallel lines. Now we can find from the total force vector the parallel and perpendicular components by taking the dot product of the force with p hat, which is in the direction that the object is traveling at any given instant in time. Remember that p hat is a unit vector, and as such, it's dimensionless. It just indicates a direction of travel. So, taking the dot product of F with p hat, we get F parallel. That's going to be the components of F along the current direction of motion. And for the perpendicular components F perp, we can just take the total force then and subtract off any parallel components that we found from F dot p hat, okay? Now, the total force is equal to F parallel plus F perp, and that, of course, by a Newton's second law, will be equal to dp dt. We can write any vector as a product of its momentum with its unit vector. So I can write, without loss of generality, p is equal to pp hat, where the p here, without the vector symbol over the top, is the magnitude of the vector p. So I'm writing the magnitude of p times p hat, and that gives me my vector p. Now, if I want to take the derivative of the vector p with respect to time, dp dt, then I'm taking the derivative of both parts of this, the magnitude of p and the direction of p, which is p hat. So I would write that as dp dt p hat plus p times dp hat dt. Now, thinking about this very carefully, dp dt, that's a magnitude. So that's a time derivative of the magnitude of the momentum. So that means that if the magnitude of the momentum changes, right, that's what that's due to. So in other words, if the speed of an object changes, then you're going to have a change in dp dt, where it's the magnitude of p. However, in this second one, it's p times dp hat dt. Now that's a directional change, because p hat indicates a change in direction. And so, if dp hat dt is non-zero, then that means that the object changed direction, okay? So, we can write it that way as F parallel being dp dt times p hat. That's going to change the speed, in other words, right? And then p dp hat dt, that's F perp. That's what changes the direction, all right? So that's how we would express that mathematically. Remember, it's the component perpendicular to the motion that supplies us with that centripetal force equation. So in this lecture. The object is to derive the centripetal force. So we're going to ignore any F parallels for now and assume that the speed of the object is constant, and that would mean that the magnitude of P doesn't change, so dp dt is 0. However, we're going to assume that dp hat dt is non-zero because we're going to have a perpendicular component of the force which changes the direction of the motion, okay? So for now, let's go with constant speed, okay? And let's derive an equation for P times dp hat dt. Okay, so to do that, we need to look at some pictures, okay? Yet again, these are from your textbook, Matter and Interactions. Let's assume that we have some object making a turn, as is shown here, but its speed is constant, okay? So it's just making a turn. All right, so it starts off with some initial momentum, kind of up and slightly to the right, and then its momentum changes a slight bit, turning by some small angle theta, and its momentum is up and to the left. And in fact, in this image, theta is exaggerated a little bit because otherwise it would be really tough to resolve and see on a slide, okay? Now, for any change in momentum, no matter how strange the path is, it could be something crazy and curly and all over the place, but if you take a small enough slice in time, then you can approximate that momentum change as a circle, and you can draw a circle that fits it over the range that you're interested in, over a small delta t. And that circle is called the kissing circle. That's a really cute name, isn't it? Okay? So we're going to assume that our angle in our little kissing circle, which is indicated by this blue dashed line in the figure, is a really small angle, okay? And we're going to assume that then we can draw the initial motion direction, P initial hat, and the final momentum, P final hat direction, and then we can draw the delta P hat this way, okay? So if this change of direction is small, then we can approximate the initial and final momentum relationships to look like a right triangle, as shown here, okay? That delta P hat then, that change in the direction, delta P hat, will be in towards the center of our kissing circle, okay? So that's the direction as is shown in this bottom figure. So that's why the delta P hat, that's why the direction of the centripetal force points in towards the center of the circle always. Okay, so now let's get the equation here. We can say that for small angles, sine theta is approximately equal to theta. That's the small angle approximation, and it's pretty common. If you're not familiar with it, you can look it up elsewhere. But you can also just plug in small angles and radians and see that it's pretty true. Okay, so sine theta is approximately equal to theta. If this is a little right triangle right here, then we can write sine of theta as delta P hat over P final hat, like so, okay? Now, this is the magnitudes of our delta P's, okay, of our delta P hat over our P final hat. That's our magnitudes. So, another way that we could write our angle theta would be in terms of the arc length subtended in our kissing circle. So, we're going to say that our kissing circle has some radius, big R, and that the angle subtended in between our initial and our final momentum is theta, as is shown here in the top of the figure. Now, the definition of an arc length of a circle says that S is equal to the radius times the angle subtended. That's just a straight up definition of arc length that you can look up elsewhere if you're not familiar with it. So I can rearrange that equation, theta is equal to S over R, where S is the arc length. Now, a distance is equal to a velocity times a change in time. Now remember, we're assuming here that our velocity isn't changing, okay, in this instant in time. We're ignoring the magnitude of dp dt changing, in other words, and we're just looking at that dp hat dt. That was our big assumption when we went into this. So we're assuming that the velocity is constant. So that means that we can write S is equal to V times delta t. Now, that S would be V times delta t divided by R is equal to theta. So that gives us our arc length. So now we have two equations for our angle theta. We have V delta t over R, and we also have the magnitude of delta P hat over P final hat. Now, P final hat is a unit vector, and it has magnitude of 1. So without loss of generality, I could say that the magnitude of delta P hat is equal to V delta t over R. And then with a little simple algebra, I can move my delta t over to the left-hand side, and I can say that delta P hat over delta t is equal to V over R. Okay? So going back to our equation for our perpendicular force and our perpendicular force only, assuming constant speed, we have P times dp hat dt, and that's our F perpendicular, okay? Now, dp hat dt, if we say that it's for a little finite time element, then we could write that as delta p hat, delta t. But that's equal to v over r, right? So now all we have to do is multiply delta p hat over delta t, which is v over r, by p. So p dp hat dt would be p times v over r, which is mv times v over r, which is mv squared over r. And that's F perpendicular, which is, of course, F perpendicular is our centripetal force. It's the force that points in towards the center of the circle and is the cause of the change in direction for the motion, for uniform circular motion. All right. That's the derivation of our centripetal force equation. I hope you understood that and enjoyed it, and I'll see you in class.